So we've heard today about production modeling is a powerful tool and that projects can use it to design and optimize their production systems. Our next speaker is going to tell us more about one application that has some new features. So welcome, Photios Ioannou. Hopefully I got that right.
Close enough.
Close enough. Okay. Photios is the professor of the Department of Civil and Environmental Engineering at the University of Michigan and a fellow ASCE. Together with his former doctoral student, J.C. Martinez, are the designers and developers of the STROBOSCOPE simulation system. He's also performed research in the development of other simulation systems. His research is in construction engineering and management in the areas of simulation, tunneling, competitive bidding models, project finance, innovative project delivery systems, and project scheduling. So well qualified to tell us, share a little bit about what he's up to and the capabilities of STROBOSCOPE now. So I'll turn it over to you if you want to share your screen.
Well, thank you very much for the invitation to make this presentation. I will try and go through the slides quickly so that we can finish on time. What I'm going to talk about is how to implement preemption in the simulation of construction operations, and in particular, how we implemented preemption in a particular simulation system called STROBOSCOPE. Preemption in construction operations, what is it? It's the interruption of an ongoing activity, and that creates the need to take appropriate actions at that point in time. Examples, there are several. For example, when equipment break down, when equipment arrive or depart, when during construction we encounter differing ground conditions, when severe weather occurs, or when activities with higher priorities need to take over the resources from other activities that need to be stopped. How do we model preemption in simulation? Well, there are two possibilities. One is without support at the simulation system level. And I can tell you from experience that modeling preemption, if the simulation system does not support it directly, it is difficult to do, and it is fraught with mistakes. And the mistakes are difficult to spot and not easy to fix. If there is support at the simulation system level, then modeling is much more straightforward. It's easier to produce correct models, and the models are more reliable. Now, preemption in simulation systems is not something new. It has been around in simulation systems for quite some time. And a particular research study that has compared simulation systems has actually graded the degree to which simulation systems implemented preemption and gave them grades from 0 to 4 out of 5. And that tells us something, that even at the system level, implementing preemption well is not easy, given that some systems got a grade of 0 out of 5. Now, the system I'm going to talk about is called STROBOSCOPE, which stands for State and Resource-Based Simulation of Construction Processes. This is a system that we developed at the University of Michigan with my former PhD student, Julio C. Martinez. Unfortunately, Julio passed away a few years ago. Otherwise, he would have been the one making this presentation. It is a general-purpose discrete event simulation system, and what's different about it is that it's based on the three-phase activity scanning paradigm as opposed to process interaction or event scheduling. Simulation model in STROBOSCOPE is represented by a graphical network, and you will see an example of that coming up, which has nodes and links. And then all the details are filled in by STROBOSCOPE statements in its own programming language. STROBOSCOPE has add-ons, and perhaps the most famous one is EasyStrobe, which is a totally graphical simulation system built in Microsoft Visio that makes the whole system easier to learn and use without too much programming knowledge. What's different about STROBOSCOPE is that you can get it for free. You can go to www.stroboscope.org and download the actual system. You will get the simulation system plus a bunch of solved examples, fully documented, so you can learn how to use it from there. And if you're really interested, there are educational videos that I created because of COVID, and I put those on YouTube, and you can see the address right there. It's just the YouTube at my first name and my last name. So what's the approach that we took in STROBOSCOPE to implement preemption. The approach is that when a trigger event occurs during simulation, then STROBOSCOPE will interrupt a particular activity instance in progress. So STROBOSCOPE needs to know which activity and which instance of that activity to stop, to interrupt. And then it starts a new activity, so it needs to know which activity to start. And that new activity takes over the preempted resources and the remaining duration of the preempted activity. This is done with essentially two new functions. The first function is called preempt, and it takes 3 arguments, as you see there. And I'll go through the example, which is easier to understand. So to preempt an activity called load, we would say preempt load. And then after that, we have load.instance, total instances minus 1, which is the number of the last instance of activity load. And then stop load is the new activity that will be started at that point in time. The second function, set time left instance, sets the remaining duration of any instance that is currently going on, and it exists in what is known as the future event list. And this one takes 3 arguments as well. The first one tells us which activity to change the duration for example, stop load. The second one tells us which particular instance of that activity. And the example here is, again, the last instance of stop load. And the 0 at the end sets the duration of that particular instance to 0. So it makes it a dummy activity. Now, in addition to the functions, there are 2 new events that occur only if the function preempt is successful. In other words, it finds an activity to preempt. And those 2 events are before preempted and after preempting. The difference between them is that before preempted takes as an argument the name of the activity that is to be preempted, current act. And it has particular timing that I'm not going to go and describe right now. After preempting takes as an argument the new activity that gets created. So, for example, after preempting the new activity, we can change its duration to 0 if we so wanted to do. We're going to go through 2 examples of preemption to see how all of this works within STROBOSCOPE. The first example is a very simple one that shows how to move soil by wheelbarrows. And the second example is one where barges arrive at a harbor and they unload using 1 or 2 cranes. Now, the first example involves essentially 2 activities called load and haul, and 2 wheelbarrows, each 6 cubic feet, and 2 laborers, 1 who loads and 1 who hauls. Now, the load activity involves taking 1 of the wheelbarrows and 1 of the laborers and loading it up to 6 cubic feet or something less, depending on which policy we implement. And the second activity, haul, takes 1 of the laborers who hauls, dumps, and returns with an empty wheelbarrow so it can be loaded again. Now, the durations of these 2 activities are L and H, and they have the same mean of 2 minutes, but different standard deviations. And as we will see, those standard deviations make a big difference. Now, we're going to compare 2 operating policies. Policy A is where a wheelbarrow is hauled only when full to 6 cubic feet. So if activity haul finishes ahead of activity load, then it has to wait for load to finish before haul can start again. In policy B, activity haul never waits. As soon as activity haul finishes, the hauler, the laborer who hauls, grabs the wheelbarrow that's being loaded, irrespective of whether it's filled up or not, and starts hauling it again. In which case, of course, the hauled wheelbarrow may not be full. Its soil in it may be less than 6 cubic feet. And the question here is, well, which policy is better, policy A or policy B? Now, if we compare the cycle times for the 2 policies, what we have are these 2 bar charts here, one for policy A and one for policy B. We have blue bars that show the load activities, load 1, load 2, load 3. And we have purple bars that show the haul activities, haul 1, haul 2, haul 3. The thing to notice is that in each cycle, the load and the haul activities start at the same time, always, and one of them is longer than the other. So the cycle time is determined by which one of the 2 activities takes longer to do. the load or the H. So it's the maximum between L and H. That gives us the cycle time. Now, if you look at production in each cycle, then what we get is 6 cubic feet divided by the cycle time, which is the maximum of L and H. The surprising thing is that for policy B, we get exactly the same production in each cycle, even though the load that gets carried is not always 6 cubic feet. So to get to the bars for policy B, we have exactly the same bars for the whole activities. They're copied down here, but they start one after the other without ever waiting for anything to finish. And the load activity has a truncated durations. That's why there is a letter T here, and that shows this load 1 needs to be truncated to the duration of hole 1, and this load 3, which is very long, needs to be truncated to the duration of hole 3. In these two cases, where load gets truncated, the amount of soil that gets loaded into the wheelbarrow is less than 6 cubic feet. So how much production do we get in each cycle? Well, if we look at this cycle right here, where load is short and hole is long, then clearly we get 6 cubic feet divided by H2. If we look at this cycle here, the amount of soil in the wheelbarrow is 6 times H over L, where H is short is the duration of H3, and L is all of this, the amount that would have been needed to load the entire 6 cubic feet. So this ratio gives us something less than 6, and then we divide the whole thing by the duration of H3. Now H3 cancels out, as you can see here, and we get 6 over L3. So in both cases, we get 6 divided by what is longer, H or L. So the production with the second policy B is exactly the same as the production for the first policy A. But this is production in a single cycle. So in each cycle, if we had 1,000 of them, each cycle would have exactly the same production per cycle. So it would seem as if though these two policies are equivalent, but that is not so. This is just a repetition of what I just told you, so I'll skip that. If we look at the long-term production for these two policies over n cycles, then for policy A, we have 6 cubic feet times the number of cycles divided by how long those n cycles took, which is the sum of the maximum of H and L over 1,000 cycles, let's say. And for policy B, we have 6 cubic feet times the minimum of what got loaded, either a full load if it's 1, or the ratio of H over L if L is longer than H, in which case this numerator will give us something less than 6n. But then the duration of the cycles is also less. It is the sum of all the whole cycles. So how do we compare these two? Well, I have tried a lot, and these two policies cannot be compared analytically, so we need to compare them with simulation. Now, to compare them with simulation and to get reasonable results, we cannot just run a simulation out of the box. We also have to implement what is known as the common random numbers variance reduction technique, so that the two policies and the productions for them will be compared under exactly the same streams of the load activities and the whole activity duration. So the Li and the Hi will be exactly the same when we figure out what is the long-term production of policy A and what is the long-term production for policy B. Now, this is a stroboscope simulation network. As I told you, a stroboscope simulation model has a simulation network that looks like an activity cycle diagram, and it has a bunch of statements that support all the details. So what we have here are the two activities. One is load right here, and the other one is haul right there. And each one of these two activities is called a combi activity because in order to start, it has to have the necessary resources. And the necessary resources are in the preceding queues. Here we have the loader queue that has one laborer. And here we have the wheelbarrow queue where we initialize the two empty wheelbarrows at the beginning of the simulation. And over here, the whole activity cannot start unless there is a wheelbarrow in wheelbarrow loaded. And we have a laborer in hauler queue. In order to make the simulation and complete it, we also have to have statements. These are examples of STROBOSCOPE statements over here that define the resources for this model. So we have generic types such as labor and soil, and we have what is known as a compound type. In this case, a wheelbarrow is a compound type that has safe props, which are properties which can change during simulation runtime. And each wheelbarrow has its own safe prop called amount loaded that holds the amount of soil that is in that particular wheelbarrow. The load and haul activities need to be defined by stating what their durations are. So the duration of load is normal with this mean and that standard deviation and that stream right there. And the duration of haul is also normal with that mean, that standard deviation and that stream right there. And here we have an event. On start of a load, we assign to something, this is an instance variable right there, which is best if read backwards. We assign to the amount loaded of the wheelbarrow currently in load the value 6. So we load the wheelbarrow with 6 cubic feet. And then another another event occurs when a resource is released through link SL2. There is link SL2 right there. So when activity haul ends and something needs to be released through SL2, the release amount is the amount loaded in the wheelbarrow in the haul instance that is terminating. Now, here is an example of haul preempts load. If we want activity haul to preempt the activity load, then we need to define a safe value that controls whether we're implementing policy A or policy B, called haul preempts load, that has the value 1. And before end of activity load, we call the function preempt with this precondition. And the precondition is that haul preempts load has indeed the value 1. And when this before end happens, then we call preempt, which stops the current instance of load. The current instance of load is the very last instance. It starts the activity stop load, which is this one right here, to which we assign a duration of 0. So stop load takes the resources from the preempted activity of load and puts the laborer back into loaded queue and the wheelbarrow into the wheelbarrow loaded. Now, the tricky thing here is that this wheelbarrow is not fully loaded. So we need to assign, before preempted load, we need to assign the amount loaded of the wheelbarrow and load, this expression. And this expression is very much like an Excel expression where we take the simulation time, we subtract the start time of this load instance. That gives us the truncated duration divided by the total duration of load. That gives us a fraction less than 1. We multiply it by 6, and that gets assigned to the amount loaded for this particular wheelbarrow. And that's pretty much how we need to implement preemption. Now, the simulation results, here are the simulation results for policy A, and if we plot them, they look sort of like this. And this is something that you should sort of feel at home with, because when the standard deviations for load and haul are small in this corner right here, then production is high. When the standard deviations are large, 0.5 and 0.5, then production is low. When we are in the other two corners, where one standard deviation is high and the other one is low, then production is sort of in between, but at the same level. So this is about as high a production as that. That is for production for policy A. Now, for policy B, the picture is kind of different. Again, we go from high in this corner to low in that corner. But if the standard deviation of haul is small, but the standard deviation of load is large, then preempting the load activity is a good thing to do. Production is high. On the other hand, in the other corner, if the standard deviation of haul is large and the standard deviation of load is small, then preemption is a lousy idea. Production is low. So if we go to the difference between the two productions, RB minus RA, we see that in this diagonal back and forth, the difference is about 0. On the left, it is positive, and on the right hand, it is negative. So this corner right here shows that preemption can improve production. In other words, RB is greater than RA, but only when whole has less variability than the variability of load. If load has less variability than whole, then preemption is not a good idea. And that leads us to the final observations. And this one is the important one. To improve production, activity load or whole with the smallest variability should work continuously. So when the standard deviation of whole is less than the standard deviation of load, then whole should work continuously. It should preempt load. If the standard deviation of load is less than the standard deviation of whole, then load should work continuously, so there should be no preemption. And looking at the time, I seem to have only 3 minutes left, so I am going to speed things up. The second example involves unloading barges using 1 or 2 cranes. So what we have here is that barges with material for land reclamation arrive at a harbor to unload. The interarrival time is exponential with a mean of 1.25 days. The unload time is uniform between half a day and 1.5 days. And the harbor has 2 berths and 2 cranes and a FIFO queue if we have too many barges wanting to unload. When 2 barges can unload, each barge unloads using 1 crane. And when only 1 barge can unload, it can switch to using 2 cranes, and its remaining unload time is cut in half. When a new barge arrives, then the barge that was using 2 cranes has to switch from 2 cranes to 1 crane, and its remaining unload time is doubled. Now, this is the STROBOSCOPE simulation model here. Again, we have an arrival process right here. Barges that arrive dock and become part of the barges that unload. And this happens only if there are berths available, and there are only 2 initially in here. And in order to unload, the activity unload has to have a crane and a barge, and that allows the activity unload to start. The thing to notice is that when there is an instance of unload that uses 2 cranes and another arrival occurs, then when that arrival occurs and the barge flows through BG3, it needs to preempt this instance of unload that uses 2 cranes, and that preemption starts this new dummy activity, restart unload, that puts the barge that was preempted back in this queue and puts the 2 cranes that were preempted back in that queue, so that the 2 barges that are here, the old one and the new one, can start 2 instances of unload. The point here is that a barge that unloads initially comes into this queue, starts an instance of unload, but then it gets preempted and it comes back to this queue and starts another instance of unload, and then it gets preempted again, goes here and starts back here. So the same barge can start several instances of unload before it finishes. Now, given the amount of time that we have, I won't be able to describe the details of the model itself in all its details here, so I'm going to skip ahead and show you the results so you appreciate at least the difficulties involved. So these are the simulation run results. So when we run a simulation, we have a bunch of barges arriving at this harbor, and this table shows the barges that arrived and unloaded, and it is sorted by the unload end time. So for each barge, we know when it arrived, how long it waited in queue before it could start unloading, when it could actually start unloading, the total time that it took to unload, which is not what we sampled. It could be less than what we sampled because part of the unloading could be done with 2 cranes. And this is when the unloading actually ended. And this is the number of the last instance of unload that finished unloading that particular barge. This is the number of times that the barge was preempted, and this is the sequence of cranes that unloaded that barge. So for barge number 2, for example, that barge started unloading with 1 crane, then it switched to 2 cranes, then it switched to 1 crane, and then it switched to 2 cranes again before it finished unloading. Now, what I want to emphasize here is that the order that the barges leave is not the same as the order they arrive. 1, 3, 2. So you see 2 is out of order here. And then we have 6, 8, 7, 9. So 7 is out of order there. And the other thing is to notice the numbers of the last instances by which a barge is finished unloading. They go 2, 4, 6, 9, 8, 10, 12, 15, 16. And again, notice that they are not in order and they skip numbers. And this is what makes preemption in this particular example particularly difficult if we do not have the new facilities that have been added to STROBOSCOPE. Now, here are some simulation statistics. Again, the first line shows the total time spent by barges in harbor, which ranges from a minimum of 0.25, which is half the time it takes for the minimum unload time, which is 0.5. So this was a barge that came, found 2 cranes, it had a minimum unload time, and it finished in 0.25 days. And the average, as you can see here, is 0.75. It should have been 1 because this is a random variable that ranges between 0.5 and 1.5. So the expected value should have been 1. However, it's 0.75 because some of the unloading was done with 2 cranes instead of a single crane. The unloading time is very similar to the in-harbor time, as you see here for the minimum time. And again, for the average, you see that it's 0.69 as opposed to 1. Again, because some of the unloading was done with 2 cranes as opposed to 1 crane. The number of barges waiting in line ranged from 0 to 4 with an average of only 5%. And the number of times that a barge was preempted was a maximum of 3 with an average of about a half. Now, the average utilization of a crane was about 42%, whereas the average utilization of a berth was less at about 29%. And the reason for that is that the cranes are kept busy as much as possible. In other words, if there is a barge to unload, both cranes will be busy, either unloading 1 barge each or both cranes unloading the same barge. And finally, what we have here is a bunch of statistics that show the percent of barges and the sequence of the number of cranes that unloaded them. So about 56%, the first 2 columns, either used 2 cranes from start to finish or 1 crane from start to finish. They were not preempted. And then the remaining 44%, all these columns over here, they had preemptions that are either 1, going from 1 crane to 2 cranes, or 2 cranes to 1 crane, or 2 preemptions, 1 to 1, 2, 1, 2, or 3 preemptions, 2, 1, 2, 1, 1, 2, 1, 2. Now, figuring all these possibilities out, and modeling all these preemption possibilities without these new functions that have been added to STROBOSCOPE, I can tell you for a fact is very, very difficult. And if you think you've done it, then you go check your results and you find out that the results are wrong because they don't match the results that you get by using the new preemption functions. And then finding out the mistake is also very difficult and very time consuming. So these are some of the conclusions that we need to summarize here. Preemption may be needed by the nature of operations. That is, we have to have them no matter what. Equipment breakdown, arrivals, departures, different ground conditions, severe weather, or activities with higher priorities are all examples. That's the nature of operations. We have to have preemption. But in addition to that, we may have preemption that is deliberate in order to improve production, as is the case for the wheelbarrows, or to reduce waiting times and service times, as is the case for the barges and the cranes. Now, the other conclusion is how to model preemption. I've already told you these conclusions. If we try to model preemption without system support, it is possible, but it's very difficult and it's very time-consuming, and the errors are hard to find and they're hard to fix. And I know this from first-hand experience. The modeling preemptions with the new functions and statements makes things much easier and straightforward. But as always with simulation models, it requires care because simulation always appears to work. It gives you results, but those results are not always necessarily correct. So one has to go back and examine the model very carefully so the results come out correct. And that's as much I would like to say in the amount of time available. So thank you, and I'll be glad to take any questions that you may have.
Okay, if you could stop sharing. Unfortunately, we've consumed more than our time, so it looks like preemption is a really important feature to have built into the modeling, and then one could explore different policies to optimize that project's or that activity's performance. I think that's the point you're trying to make.
I am.
Okay. Well, thank you very much for preparing the paper and making the presentation. And to keep things on, move on to our next speaker.
Well, if there is one thing I could add, if anybody wants this model, send me an email and I'll send them to you.
All right. Very good. Thank you.
Thank you.